Well, so you've learned about some series, some different kinds of series in section 8.2. And, but there's a lot of other kinds of series too. And when we have a series, we are interested first if the series converges or diverges. Now, if the series converges, then we want to find its sum. And in fact, there are many series where you can actually find a sum for the series. Like, for instance, a convergent geometric series or a telescoping series. Those series you can find sums to. And there are other series that you can actually find sums to, true sums. And of course, if for some reason you can't find the exact sum of a series, you could approximate it, okay? And, and so section 8.3 talks about just some different kinds of tests that can be used to determine if a series converges or diverges. And what I'd like to do is go through the ebook and show you the different tests. And then we'll go ahead and look at some examples here. So first test is called the integral test. And actually, let me take off some of the highlighting here. So the integral test relates to an integral. How many remember remember your improper integrals from section 5.10? You should remember them, right? You just were tested on them. But okay, Jacob remembers, and so it turns out that there is a connection between the convergence or divergence of an improper integral and the convergence or divergence of an infinite series. So if you have a function like that's continuous, positive, and decreasing over the interval 1 to infinity. So what I'm looking at here, and maybe I'll just take a little more of the highlight off here. They say, suppose that you have a decreasing function and let the terms of your series a sub n be equal to f of n. If that's the case, if that's the case, then the series is convergent, okay, if and only if the improper integral is convergent. Okay, so this makes some bit of intuitive sense. If the improper, so like in part A of the integral test, if the improper integral converges, okay, then the series converges. Part B says if the improper integral diverges, then the series diverges. Okay, and the idea, if I were to just sort of give you a little feel for why this is true, if we look at, for instance, if we look at this series here, okay, the series n equals 1 to infinity of 1 over n squared. Okay, those are the terms of the series, 1 over 1 squared, plus 1 over 2 squared, plus 1 over 3 squared, and so forth. Well, what you can do is you can actually view those terms of the series as areas of rectangles. So here in figure 1, they have a picture of the function 1 over x squared. And the little blue boxes are, you notice every rectangle has a width of 1. And so the height of the rectangle is equal to the, it's equal to a function value. So like, for instance, at 1, when x equals 1, the height of that rectangle is 1 over 1 squared, because the function that touches the corners is 1 over x squared. So when x is 1, the height is 1 over 1 squared. Well, that means the area of that rectangle would be the height, 1 over 1 squared, times the base, which is 1. The next area is has a height of 1 over 2 squared. Okay, you can see when x equals 2, the rectangle touches the function, and so it has a height of 1 over 2 squared when x is 2. And 1 over 2 squared times the base of 1 is 1 over 2 squared. So you see, if you just ignore, like if you don't worry about the 1 over 1 squared, I mean that equals 1, right? But look at the rest of those rectangles that have areas 1 over 2 squared, 1 over 3 squared, 1 over 4 squared, 1 over 5 squared, and so forth. Those are the terms of the series. Well, you see, if you add up those areas, the sum of those areas has to be less than the area under the function 1 over x squared. So if the improper integral from 1 to infinity of the function 1 over x squared were to converge, which it does, that means that then the sum of the terms of your series also would have to converge. Okay, they would have to converge because those areas are less than the area of the improper integral. Okay, so you see, they say here that what I said, that the sum of the area of the rectangles is, as you see there, and of course, if you were to compute the improper integral from 1 to infinity of 1 over x squared dx, that would be 1. Okay, so 1 over 1 squared, which is the first term of the series, plus that improper integral will equal 2. But of course, our series isn't equal to the improper integral. The sum of the terms of the series, the sum of the second term, third term, fourth term, and so forth in the series is not equal to that improper integral. It's less than that by virtue of the picture in figure 1. And so the sum of our series, okay, has to be less than 2. Okay, it has to be less than 2. And so therefore our series diverges, or converges. So the point is, the fact that the improper integral converged, okay, the improper integral of the function 1 over x squared from 1 to infinity, the fact that that series, that improper integral converges, tells us that our series, starting at n equals 2 to infinity, our infinite series, that would converge also. And then if you add 1 over 1 squared to that, well, you're just adding a finite number. That series then, full series, converges. And that's the idea. Well, 2, Sophie, because if you look above, this sum here equals 2. And the improper integral contains more area than our series does, starting with the second, third, starting from the second term onward. So that's why they say this. It really, if really looking at the picture in figure 1, it'll help you get a feel for what they're talking about. This then reinforces the idea of the integral test. Okay, so okay, you're welcome. You're welcome, Sophie. So those improper integrals, they're back. They're back. We can't ignore them. So that's the integral test. Now, there are some results here that are important. By the way, the integral test says that you don't need to start the series or integral at n equals 1. If, for instance, if you were to test the series n equals 4 to infinity of 1 over n minus 3 cubed, if you were to test convergence or divergence of that series, well, you could see if the improper integral from 4 to infinity of 1 over x minus 3 squared dx, you could see if that integral converges or diverges. Okay, so it doesn't matter What matters is how the series behaves as you move out to infinity. Just like an improper integral, its convergence or divergence determines the convergence or divergence depends on how the improper integral, how that function behaves as you move out to infinity. Is the, how is the area, how does it accumulate? Does the area, the area accumulates, but is the area dying down at a fast enough rate so the improper integral converges? It's the same kind of thing with the infinite series. Did the series die down fast enough so that as you move out to infinity, so that that series converges? Same kind of principle. And there is an important series called the P series here that they prove it in the book, but the P series, okay, let me just, hold on, I have it highlighted, but let me just see if I can make that. No, I got to highlight it, okay. And let me take off, okay, so the P series is a series where n equals 1 to infinity, but you don't have to start at n equals 1. Okay, you could start at n equals 100 and you'd still have a P series. But the series, which is the terms are, and the series are 1 over n to the pth power, that will converge if p is greater than 1, and it will diverge if p is less than or equal to 1. So this is no different than if you have the integral of 1 over x to the pth power dx, where your limits are 1 to infinity. That improper integral would converge if p is greater than 1 and diverge if p is less than or equal to 1. And they give an example here of a series where this series here, this P series, is convergent. The series n equals 1 to infinity of 1 over n cubed, okay, that's a P series. It's not a geometric series. It's not a telescoping series. It's a P series, and it converges because P equals 3, which is greater than 1. But on the other hand, if you were to have a series like this, series 1 over n to the third power, which is the cube root of n, there p is equal to a third. And since a third is less than 1, that P series diverges. Okay? That P series would diverge. Okay, so P series are very helpful because a lot of times what we want to do is we want to compare a difficult series to a P series to see if the series converges or diverges. And as a matter of fact, then, this brings us to something called the comparison test. Okay, and again, I want to take off some of the highlight there. The comparison test says suppose you have a series, okay, with positive terms. So the series that we're dealing with in section 8.3 either are going to have all positive terms or all negative terms. But I think for the most part, the series they deal with are all positive terms. Because a series with all negative terms, you could just factor the negative out, and then you'd have negative times a series with all positive terms. Well, if a series has all positive terms, okay, let's say you have two series, a series A sub n and series B sub n with positive terms. Part A of the comparison test says that if, let me just highlight it in pink here, if your series B sub n is convergent and the terms of the series A sub n are less than B sub n, then the series A sub n has to be convergent. Okay, so the series B sub n, if it converges, it's going to be some finite positive number. Well, if the terms of this other series are smaller, okay, then that series also has to converge as well. Okay, because it's bounded by the sum of the larger series. Does that make sense in part A? Does that make reasonable sense? Is it intuitive? Okay, Jacob feels good with it. And Leping is good. And Tall, all right, good, good. All right, well now let's look at part B. Part B says, okay, what if you have a divergent series? Okay, what if you have a divergent series? What if your series B sub n is divergent and the terms of the other series are greater than the terms of the series in B sub n? Well, then that series has to diverge because that series would have to be larger. So that's called the comparison test, and it's very useful when we have series whose terms are all positive. Okay. Okay. Are there any questions on that? Okay. Well, let's move on then. Let's move on. We will look at some examples. Okay. We have a test called the limit comparison test. This is another test. Okay, again, what you have is normally you have a difficult series, and what you're trying to do is relate that difficult series to an easier series that you know something about, like a P series. Okay, so if, for instance, you have two series, and you take the limit of the terms of those series, and the ratio of the limit, or the limit of the ratio, is equal to a constant, where that constant is some finite number, then what you're saying is that the terms of the series, of both series, as you move out in the tail of the series, as you move out, as n goes to infinity, the terms of the series, when n is large, the terms of the series are essentially in proportion to each other. Because if an over bn, if the limit is equal to a constant, you're saying essentially that the terms of the series are proportional to each other. Okay, so like for instance, if an over bn, if the limit were equal to 1, you'd be saying that the terms of the one series are basically the same as the terms of the other series if you move out far enough in the series. So that means the behavior of one series, whether it converges or diverges, would be the same then as the behavior of the other series. Convergence of one series means convergence of the other series. Divergence of one series means divergence of the other series. Because the two series, the terms are proportional to each other as you move out in the series. The one series effectively acts like the other series. Well, yeah, it acts like it. It's just the terms are in proportion, but so like for instance, let me give you an example here of that. Let's say you have okay. Let's say you have this series here, the harmonic series. Okay, which is 1 plus a half plus a third plus a fourth. Okay, let's say you have a harmonic series, and let's say you have another series, this series here, 1 over 2n. We actually talked about that, but let's just go ahead and write it out here. Let's look at the terms of the series one by one. First terms of the series. Second terms of the series. third terms of the series, fourth terms of both series. Are the terms in proportion to each other? Are the terms of these series in proportion to each other? Yes, they are. In fact, what's that proportion going to be? If we take the limit as n goes to infinity of an over bn, and let's say an is the 1 over 2n, and let's say the bn is 1 over n. Oh, hold on. I forgot. One moment. Good, Renaud. One moment. I forgot to carry my limit. Okay, so 1 over 2n and 1 over n. So this is 1 over 2n times n over 1. And what's this all equal to here?
So you're considering a of n to be that second one and not the first?
That's correct.
Okay.
That's correct. So what I'm doing, good question, Maria.
I was just confused because normally when you put things down, a comes first.
Yeah,
Okay.
well, the reason I'm doing it this way is this is the harmonic series. And the harmonic, but a harmonic series, I know something, I know it diverges. The second series here, well, you know, okay, you know, what's this series do? What's the series going to do? Okay, so what I do is I tend to put the terms of the series I don't know about in the numerator, and I then compare it. You know, that's my central focus, is the terms of the series I don't know about. I don't know how that second series behaves. So that I let that be the a sub n term, and then the b sub n is the term of a series that I know something about, the harmonic series. And so what happens is when we take the limit of this, what do we get? What's 1 over 2n times n over 1? What's that equal? A half. That's right. So the second series here, the second series, the terms of that series are proportional to the terms of the first series. Okay. And in fact, it's a half. And we can see that. We can see that the terms of the second series here are half as large as the terms of the first series. Now, that doesn't have to be the case. I mean, you could have, I mean, I picked a nice, easy example, but you could have it where, you know, you don't have that relationship until you're later in the series when n goes to infinity. But the point is, for like you can see, do you see that since the terms are in proportion to each other, that the behavior of the harmonic series then determines that this second series also has to diverge. Because really the second series is just a half. The second series is just a half times the first series. That's what it is. Okay, so that's I mean, are we okay with that? Are we okay with that? If you have a bad series, half of a bad series is still a bad series. You know what I'm trying to say? I'm trying to sort of bad series, I mean like divergent, you know. If you eat an apple and the apple's bad, okay, if you have a bad apple Is half of the bad apple still going to be bad? If you have a rotten apple, is half of the rotten apple still going to be rotten? Yeah, same kind of thinking. Okay, so Tal, you had a question? You're good? Oh, I think you were just replying. Okay, all right, all right. So so this means then that's the limit comparison test. Let's move on. Let's move on. Let me go back to, just want to pick a nice, easy example for you. Examples, you know, I like to think of intuitive examples. Then I appreciate these theorems. Sophie, I'm considering divergent as bad because divergent series, you know, they're not very interesting. It's not very interesting if a series diverges. It's much more interesting if the series converges to a finite number. But I was just trying to, I mean, I guess divergent series aren't bad, but they're not very useful. Let's put them that way. Let's put it that way. All right, good, good. Let's go on here. Okay, so now another theorem too is estimating the sum of a series. Okay, so remember, if you have a divergent series, or I'm sorry, convergent series, that means that series has a finite sum. And we want to be able to get an idea of what the error is, or remainder estimate is, for this finite sum. In other words, I want to be careful here. I'm not saying this right. If you have an infinite series, okay, and you know the series converges, okay, in order to estimate that series, if you don't have a formula, you're going to have to use a computer and add up the first like billion terms, okay? But maybe add up the first 100 terms, okay? Well, if you were to add up the first 100 terms of the series, okay, that 100th partial sum would not be the exact same value as the series. Okay, well, how far off would you be? That's called your remainder estimate. And the remainder for the R sub n, it turns out, can be, there's a remainder estimate for the integral test says that the nth partial sum, the error in the nth partial sum, to that approximation of the true sum would be between these two integrals. Okay, and of course, what's more interesting is the integral on the right, because the integral on the right gives you an upper bound on your error. Okay, and that's called the remainder estimate. So these are the theorems, the ideas behind section 8.3. And what I'd like to do now is look at some examples with you. So the book has good examples, but let me just go ahead and bring up some of my examples here. Some are which from the book. Let me give you a moment to copy this example down. Okay, so let's take a look here at these series. So series A, one moment here, one moment. Sorry, class, one moment, one moment. Get back. Okay, so series A, let me ask you. So are the terms of this series in A getting smaller with N? Are the terms getting smaller? Okay, and what are the terms, good, what are the terms approaching with N? When I say getting smaller, the terms are approaching what number with N? That's right, 0. So the series has to do that to have a chance at converging. Now notice I said to have a chance at converging. Series could get, the terms of a series can get smaller, they can approach 0, but yet the series diverges, like the harmonic series. So let me ask you a second question then. Do you think the 4 over n, the 4 times n and the 3, well, on the denominator you have a 2n squared, you have a 4n, and you have a 3. Okay? A 2n squared, 4n, and a 3. So, well, all right. So for those terms, what's like the dominating term as n gets large? What term dominates? That's right, Nicole. The 2n squared. That's right, Sophie. The 2n squared. So the 4n and the 3 aren't really going to matter a lot when n's very, very, very large. Okay, so this series, intuitively, when n is large, this series sort of behaves like the series 5 over 2n squared when n is large, right? I mean, we could intuitively reach that, right? We can intuitively think about that. So what I'm going to do is I'm going to actually make a comparison here. All right. So let's go ahead and look at the solution. So for n greater than or equal to 1, our series, the terms of our series here, okay, which are 5 over 2n squared plus 4n plus 3, that's less than 5 over 2n squared. Now, why am I interested in 5 over 2n squared? Well, if we look at the series from n equals 1 to infinity of 5 over 2n squared, we can factor 5 halves out. And so the series 5 over 2n squared equals 5 halves times the series 1 over n squared. But that's a convergent piece, that's a convergent series. Because all this is 5 halves times a convergent piece series. Let me give you a moment to catch up here. Let me know if you have any questions. Okay, so, all right. Are there any questions up to here? We're not done yet. We're not done yet. But what do you think is going to happen to our series? Do you think our series is going to converge or diverge? That's right, Renat. It will converge. Let me go to the next page then. So by the comparison test, if the larger series converges, which it does, because the larger series, I mean, we established, if again, let me just go back. Here's the you know, how we started. The 5/2n squared, those terms come from the larger series, and the larger series converges. Therefore, the smaller series with the terms 5/2n squared plus 4n plus 3, that series has to converge as well. All we're doing here is we're establishing convergence. We're not finding the sum, but we're just establishing convergence. So by the comparison test, if the larger series converges, then the smaller series also converges. And now the fact that the smaller series also converges, to figure out what that series converges to, you could get a book on different types of infinite series and what they converge to. There's a whole book written by Conrad Knopp on that kind of topic. Or you could use a computer to try to get an estimate on the series. Question, let's see, hold on here. I heard a chat, hold on here, I heard something. Oh wait, hold on. So Nathan says we won't be asked to find the sum of a series like this one. No, Nathan, you would not. You would not. You just need to know if it converges or diverges. Now, I want to be careful. You could be asked to approximate the sum, okay, but I'll show you how to do that. Are there any questions on this first problem? How many are feeling good so far? Okay, Nicole's good, and you know, we're trying to use our intuition here. And Renard's good, okay, very good. A few other folks, all right, and Tall's good, wonderful, wonderful. All right, well, let's go now to the second problem. Okay, so I'm looking at this series. You know, I'm looking at this series here. And what does this series kind of behave like when n is large? What does the series sort of behave like when, you know, I'm sort of, when n is large, yeah, the series sort of behaves like the series n squared over 3n to the fourth. Good. Okay. So, all right. Well, I'm going to use the comparison test here. I'm going to use the comparison test. Okay. I'm going to use the comparison test. So here we go. When n is greater than or equal to 1, okay, which is the terms of the series. Well, the terms of the series are n squared over 3n to the fourth plus 1. Okay. Well, that is less than n squared over 3n to the fourth plus 1. But then that term is less than n squared over 3n to the fourth, which is 1 over 3n squared. So by the comparison test, our ugly series here converges by comparison with the convergent p-series. The convergent p-series is bigger. Because the terms of the convergent p-series are bigger. In other words, I mean, effectively what you're saying is this. Here's what you're saying. Maybe I'll write it below. Okay, so that's what you're saying. The second series is greater than the series 1 over 3n squared is greater than the other series. So, and we know that all the terms are, basically positive. So if this series converges, if the larger series converges, what's the smaller series got to do?
Converge.
That has to converge too. Right. What else can it do? Right. Now I'll note that this series is positive, right? It's greater than 0. I mean, you have to have terms that have a series that have positive terms. Okay, so there's the value of the comparison test. Okay, let's go ahead and look at a few more problems. Are we good? May I move on? Okay, Tall's good. Nathan's good. Jacob's good. All right. Okay, let's move on then. Very good. Nicole's good. Let's move on. Okay, a couple more problems. Okay, let me give you a moment to copy these examples, this example down. Okay, so, well, let's look at this first series here. Let's look at this first series. So does the -1 here, is that going to matter when n is large, that -1 in the denominator? No. So we really can think of that's right, Nicole. That's right, Sophie. We really can think of the series as a series of, 1/2 to the nth power. Okay. So what does that remind you of? 1 to the 2nth power. What kind of series would that remind you of? Geometric. That's right, Nicole. So we know that the geometric series is going to get involved in here somehow. Well, let's go ahead. Do you want to try the comparison test? Who wants to try the comparison test? Give me a thumbs up. All right, Jacob's liking that. All right, and Sophie likes that. All right, well, let's see. Let's try it. So here we go. So the 1/2 to the nth power minus 1 is greater than 1/2 to the nth. Okay. And the 2 to the nth power is a larger denominator than 2 to the nth power minus 1. Okay. But and so, okay, how am I going to use the series 1/2 to the nth power? Okay, well that's the same as the series 1/2 to the nth power, which is a convergent series. It's a convergent geometric series, right? So what I like, I'm trying to show you what thought processes are going on here in my mind when I do these kind of problems, and I want to share them with you. I mean, that's that's what I like doing, and that's what I do. So, but in this case, the fact that geometric series converges isn't going to give us any information about the series that we're interested in. Now, why is that? Why doesn't it give any information? Well, okay. So here in this case, I think we agree that this is a true statement. Okay, the series that we're interested in is larger than that geometric series. Okay, but and the geometric series converges, but our larger series could be finite or it could be infinity, right? If the smaller, so we can't use the comparison test here because we are comparing our series to a smaller series that converges. So we can't say that our larger series converges. It could converge, but it could diverge too. It could be, the sum could be equal to infinity. Does that make sense? Okay, Leping's comfortable with that. Okay, so comparison test didn't work. What other tests might work that you learned about? It has the words comparison test in it, but it has a name before comparison test. Begins with an L. Right, good, Sophie, the limit comparison test. Okay, so let's look at a limit comparison test. Are there any questions before I move on?
Can you hold on just one more second?
Sure, sure. Let me know if you have any questions.
Thank you.
You're welcome. All right, is everybody good? Give me a thumbs up if you're good. Okay, good. Nathan's good. Okay, excellent. Everybody's good. All right. Let's use the limit comparison test. We'll let a sub n be 1 over 2 to the nth power minus 1, and b sub n will equal 1 over 2 to the nth power. So I take the limit of the ratio. Okay, and, well, hold on. Yeah, if I were to put in an extra step here, this is the limit as n goes to infinity of 1 over 2 to the nth power minus 1 times the reciprocal 2nth over 1. Which gets us here. Now what I can do is here, I can multiply the top and bottom by 1 divided by 2 to the nth power, which is just 1, right? And that's going to get me here. And now I can see that the limit of the ratio is equal to 1, which is greater than 0. And so the limit comparison test is going to work here. The limit comparison test is going to work. It's going to work just fine. Okay. Are there any questions? What I put in red, Sophie, was I wanted to show you how 2n over 2n minus 1, or sorry, 2 to the nth power over 2 to the nth power minus 1, how that became 1 over 1 minus 1 over 2 to the nth power. So I just put this in like, hey, you know, I'm multiplying the numerator and denominator by 1 over 2 to the nth power, you know, but the whole thing is just 1, right? And so it's trying to justify that next step there. Okay, you're welcome. Well, Nathan, this is what this means. Okay, it means that the two series eventually are going to be very similar to each other, because we got a 1, right? We got a 1. We got a 1 as our constant. That's our C, the 1. So that means that these two series eventually, the terms of the two series eventually are going to be the same for both series. So the behavior of the one series is equivalent to the behavior of the other series. Convergence of the one series means convergence of the other series. And that's then what I'm saying here. So I'm trying to, how many find these, this kind of, the words, these kind of explanations where I write out like what's going on in my mind. Is that helpful? Is that helping you get a feel? Okay, wow, okay. Excellent. Thank you. Wonderful. I mean, I know when I took math, I don't believe my professors did that. But you know, that's okay. I don't have to. I can do it my way, right? And all right, may we go now and look at the second example? We're good? All right. Okay, well then let's go look at this second example here. So, all right. Here's the series. So what would be helpful to have for this series? What would be helpful to have? They wrote out some terms of the series, 1 plus a third plus a fifth plus a seventh plus a ninth and so forth. Yeah, a formula. Okay, so what do you think the formula is? What do you think the formula is for this series? If we were to hold on, Leping, let's see. Leping, you're right. That's the formula. That series can be represented by the summation where n goes from 1 to infinity of 1 over 2 times n minus 1. Does the 1 matter much as n goes to infinity? Does that? No. So you're kind of focused. Okay, good. You're kind of focused on this part then, right? So what do your instincts tell you about this series? Do you think it'll converge or diverge? Okay, Nathan's thinking diverge. Nathan says it's like a harmonic, and that's right. That's right. Renaud says diverge. All right. Okay, so let's go ahead and get to the answer. I'm going to use the limit comparison test. So what happens is the regular comparison test, if I can't easily use the regular comparison test, okay, then I, like, you know, that -1 down there in the denominator can make it a little difficult to use the comparison test. I mean, I mean, I'm not saying, I haven't really examined it to see if it would work, but, you know, I'm just going to use the limit comparison test. So a sub n is 1 over 2n minus 1. B sub n is 1 over n. Okay, now, why am I picking 1 over n? What am I comparing this series to? What am I trying to relate this series to? What kind of series am I trying to relate it to? That's right, Sophie, the harmonic series. And the harmonic series is this series. So, that being said, we'll do the ratio test, and we end up getting a half when we take the limit of the ratio of a sub n over b sub n. Let me give you a moment to catch up. Please ask questions if anything's unclear. Yes, Marcus.
Professor, so in general, does it matter like which one uses AN and BN?
It doesn't.
It doesn't.
It doesn't. I just traditionally like to let a sub n be the nth term from the series I'm interested in, and then b sub n be the term from the other series. That's just kind of how I do it. What do you students say? That's how I roll. How many have heard that expression? I don't know. Is that still used? That's how I roll. Okay, Sophie uses that expression. Okay. Jacob, all right, good. So I'm trying to, you know, I gotta, you know, have to stay modern here. You know, have to stay modern. Okay. So I have Netflix like you all have. You probably all have Netflix, right? All right, just got that recently. So, you know. All right, so let's now go to the next page if we're good. So this is our C then. The 1/2 is the C. So therefore, the series, our series, eventually behaves like 1/2 times the harmonic series. Eventually, I should probably say, to be more exact, the terms of our series eventually behave like 1/2 times the terms, let's see, the terms of this series. So therefore, the terms of the series eventually, we're in that R series, eventually behave like 1/2 times the terms of the harmonic series. And so since the harmonic series diverges, our series diverges. And so, you know, it wouldn't be useful trying to, figure out the sum of that series because it diverges. Sure. Sophie, you want me to go back to the previous page?
Yeah, once everyone finishes getting this.
Okay, I'll go back. We'll go back in a moment here. Very good. Let's see. Sorry, Marcus is asking, hold on here. One moment. Okay, why did I do the 1 over n? The reason is because I want to compare this series that I have to a harmonic series. And the harmonic series, the nth term of the harmonic series is 1 over n. So that's where I'm getting my d sub n from, Marcus. Okay, so you got to kind of come up with it. You have to kind of come up with it, but does that make sense, Marcus? Does that make good sense? I have to compare my series to some other series. I'm choosing to compare it to the harmonic series. And the harmonic series, the nth term in the harmonic series is 1 over n. That's why I got the 1 over n. So I'm not taking I'm not like well, the series 1 over 2n minus 1, the negative 1 here, that's when n is large, that's not going to be a big influence, right? So I'm focused on 1 over 2n. Well, 1 over 2n is just 1/2 times 1 over n. Okay, and that kind of clued me in to make a comparison, a limit comparison with the harmonic series. Okay? Let me go back one page here. Sophie, I've gone back one page here.
Okay, thank you. Just give me
Sure.
a second. Can you explain the bottom portion one more time?
Okay, the bottom portion, like this part here.
Yeah.
Okay, so all right. So what I do here is
I understand how you have a 1 a sub n over b sub n, but like from there on, how did you get n over 2n minus 1?
okay. What I do is here, right here, I multiply. No, hold on. Let me put in an extra step here. So think of multiplying by the reciprocal.
Oh.
And that gets you n over 2n minus 1.
Okay. I see.
Okay?
And then from there on, you.
Oh, and then here, I multiply here by 1 over n on the top, 1 over n on the bottom,
Okay.
which is equal to 1. And that's how I get there.
Okay.
All right, very good. Let's see, Renaud asks if we are comparing to a divergent, let me see here, let me go. All right, very good. Hold on, Renaud, let me get your question here. Renaud asks if we are comparing to a divergent series, the number we get from the limit is just a factor. That's absolutely correct, Renaud. That's absolutely correct. That's exactly right. Very good. Well, now Marcus, did you hear remember the discussion we had on the harmonic series a little earlier in the class? You remember that? We talked about the harmonic series, and yeah, that's right. So I mean, it is sort of counterintuitive, right? How can you have a series where you're adding terms that are getting smaller and smaller and smaller, approaching zero, and that series still diverges? It's counterintuitive, but in fact, it can happen. And it does happen. And, you know, it makes our lives a little more interesting, right? But right. Marcus, I'll hang out a little bit after class too, if you want to talk about that more, okay? Good question. Let me bring up the ebook again. Okay, you're welcome. I want to look at one example from the ebook. Here. Okay, one moment here. Okay, so I want to do an example with the integral test. Okay, so this is the integral test, which we looked at before. And if we go down a little bit here, they have an example where they use the integral test. So in this problem, they want you to determine if the series n equals 1 that goes from n equals 1 to infinity of log n over n converges or diverges. Now, this is a type of series where it would be difficult to use a comparison test or a limit comparison test because of what makes that series sort of difficult what's making that series difficult for using the limit comparison test or the comparison test. I'm not saying it can't be done, but what's making it difficult in that series? The logarithm. That's right, Sophie. So in this case, well, let's try the integral test. Well, the integral test says above that you have to have, okay, a function that's continuous, positive, and decreasing. So our series here, this series, if we take the derivative of the function, the log of x over x. So again, what you're going to do is you're going to look at the log of x divided by x, and you're going to take the derivative. Because you take the derivative to establish if the function's decreasing. Is f prime of x less than 0. And in fact, if you take 1 minus the log of x over x squared, that function is going to be decreasing when x is greater than e. Okay, now why is that? Why is that? Let me show you why here. Let me show you why. So this is for example 1. Okay, example 1 from section 8.3. So f prime of x is equal to 1 minus the log of x over x squared. Okay, so we want to know where is this derivative less than 0? Okay, and we're assuming that x is going to be greater than or equal to 1. Well, the denominator is never 0 if x is greater than or equal to 1. So the derivative would be negative. That when that's negative, that's dependent on the numerator being negative. Well, when is 1 minus log of x negative? When's it less than 0? It's negative when 1 is less than the log of x, okay, or when e to the first power is less than e to the log of x. And this means then that, well, what's e to the log of x power? What's the right-hand side going to be of this inequality? You know what e to the log of e raised to the log of x power. That's just x. That's right, Michelle. So x is greater than e. So this function, which was the log of x over x, decreases for x greater than e. Okay. So that means that eventually the function will be decreasing. So it doesn't matter that what the function's doing from when x goes from 1 to e. It doesn't matter. That in other words, what I'm trying to say is I mean, if you like, so e right is 2.7. Gosh, I should know that. I think it's 2.718. Hold on, second e to the first power. Yeah, 2.718, and then it keeps going, right? But it's about 2.718. So the improper integral, I mean, the fact that the function is eventually decreasing means you can use the integral test, okay? So that being said, let's go back to that example 1. That being said, we'll use the integral test. And when we use the integral test, we determine that this integral, okay, we take the limit as t goes to infinity of the proper integral that goes from 1 to t. You know, they leave out a step there, you know, but they get the antiderivative, and you're going to get infinity for the improper integral. So the improper integral diverges, and you've done enough improper integrals. You know, obviously they let u equal the log of x, and you do a substitution to get the antiderivative there. So that improper integral diverges. Okay, and so therefore our since the improper integral diverges, that means our series diverges also by the integral test. Okay, so when you do these problems, okay, it's not like one size fits all. You for different types of series, you'll use different approaches, and you've learned some approaches here in section 8.3: the integral test, the comparison test, and the limit comparison test. And then you also have, don't forget, the test for divergence back from section 8.2. And you also know about like geometric series as well, and telescoping series. So you have a lot of tools here to analyze series. Are there any questions before I stop the recording? Okay, how many are feeling comfortable? I mean, maybe not 100% comfortable, but reasonably comfortable, feeling okay with the concepts. Okay, Sean's feeling reasonable. Nicole and Baraka and Leping, and I think there were a few others there. That's excellent. All right, well, let me stop the recording then.